Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so today we're very pleased to have Tonghai Yang visiting us from University of Wisconsin. Tonghai is a great friend and collaborator for a long time, ever since we were postdocs together at University of Michigan. He was a postdoc at University of Michigan and at the Institute for Advanced Study in Princeton. He was the winner of the AMS Centennial Fellowship at Harvard in 1999, along with a number of other awards and incredibly prestigious and complicated articles and books that he has published on the subject of arithmetic geometry. So we're very pleased to have him visiting us here for the first time. He'll be speaking to us on some work that's very close to my own interests and related to genus 2 cryptography. But I should also mention he's also the founder of a very successful charity organization called Hometown Education Foundation, which he'll also tell you about.
Okay, thank you very much. Thanks, Christine, very much for the invitation. It's great to be here. It's great to see Microsoft in person instead of on computer. So this is just, I want to give a 1 minute or 2 minute brief introduction to this charity called Hometown Education Foundation. It's established in 2004 to help the poor kids in my home county in China, a rural area, to help them just finish their very basic elementary through high school education. Because they have to pay for their books and also some other fees. Unlike the US, if you are poor, you don't pay anything, you're totally free, they have to pay. And some of the kids don't have money to pay and they're in danger of dropping out of school. And really pretty minimal, actually. Elementary school about $50 a year, and middle school about $80 a year, and high school a little bit much more expensive. But it's very hard to get to high school too. It's not totally free. You need to take a competition to get to the high school. Only about 60% of the rural area, about 90 or 80 to 90 of the city people go to high school, but only about 60 rural people go to high school kids. So I hope you can help us to buy just donations, and we don't take any overhead. But all the money you donated, we will give to the students. I pay all the overhead here. My colleagues there pay all the overhead there. And you also help us using goodshop.com. That's just the web page where all these online stores there. You just there. Once you go there, just indicate you support Hometown Education Foundation and just verify it. And just from there, you shop as usual. You don't do anything else. It's free. And every time you do, they will pay probably 1% of proceeds to us as a donation from them. So it's also very nice, typical Amazon.com, Travelers.com, or theirs or the other companies, eBay or there. And also Microsoft is very nice. I have this matching up program as you already know. And you donate $1, they give another $1, so $2. It's very good for the kids. Thanks a lot. That's this. Now here's my math talk. To make it bigger. Okay. So I will talk about the arithmetic intersections, and the motivation is conjecture of Christine years ago. So she was very nice to explain that to me. We tried to work it out. Someone got stuck in the middle.
Sorry, can you make it full screen, please?
Say it again?
Can you make it full?
Oh yeah, okay, sure. Yeah, I forgot about that. Not a very.
Press Control N.
Okay, this is good now. Oh, still bigger? How to get it all bigger? Control L?
Yeah. Why don't you do a slideshow? Yeah, Control L.
Okay, good. Okay, so the basic idea we'll try to start with cryptography, the cryptography system. I have no idea what I'm talking about it. But I heard that the basic idea for the discrete logarithm cryptography is if you give an abelian group, you consider the equation n p equals q. Then if you know p and you also know n is sort of easy to figure out your addition, so very simple to get a q. So that's a good part. The even better part is it's hard to find n if you know p and q. So somebody cannot break it, even they know p and q. Okay, so that's the idea. So what you do in that case will be, the difficulty depends on the biggest prime factor of the order of g and the operation on g. Because if operation is complicated, of course, it will be more expensive. So practically, that's important too. So one thing to do for a mathematician will be to find a good abelian group, such that his order is a big prime, or a big prime times a couple of very small primes. So you can save the storage and this money. You can save. Second thing is the operation on G is have to be both hard, mean be more secure, and also easy, more efficient. The balance, I guess, is very important practical questions. So here is what you want to do. And so how do you get that group? So classical group, I think probably the first public key or cryptography started with this. They have a lawsuit between this one and RSA. G equal to the, yeah.
Sorry, that's Diffie-Hellman, not RSA.
Huh?
No, he didn't say.
It's not RSA, this is Diffie-Hellman.
Yeah, this is before. And I think they have a patent lawsuit. Well, my former teacher was expert on witness. And this is a FP star. And the other one will be more, the other one is a technical curve, E. And look at his rational points. And that will be a abelian group. It hopefully be a prime order, that will be cyclic, that will be very nice. If you take it a curve, that's the one-dimensional project space with additive group structure. You can also think, well, what about take abelian varieties? So the mathematicians don't prevent them to do that. So A is an abelian variety over FP. Okay. So the problem with on the general abelian variety, you have lots of them. It's great. You can produce a lot of them. The problem is sort of hard to describe. The universal curve is very simple. It's just y squared equals fx, and degree 3. Just write them down. So very easy to write down. You don't need geometry. Just go write them down. But in general abelian variety, you cannot write them down. It's hard dimensional things. Second, it's hard to determine or even estimate his rational points. How many are there? It's not a trivial thing. Very hard thing. Depends on the frobenius are there. Okay, so how do you solve these problems? Around 90s and early 2000s, and this person Spanak, and also Van Vermeulen in the mid 90s, and also Henry Cohn and Christine, that's in the Microsoft, and then when around 2000 he found you can do that using Jacobians of CM genus 2 curves to overcome these difficulties. In other words, you take a genus 2 curves. If his Jacobian have complex multiplication, I will define it on. Just have more structure. If you take a general abelian variety, it's very hard. But if you know it's a Jacobian, it's sort of easier. But if we want to be even better, you want to be extra symmetry. So extra structure there, they'll be easier to control. That's basic idea is if you don't know the same, don't worry about it, just extra structures. So let me try to explain what the CM abelian variety is. I started with a real quadratic field. The Q Jordan square of D is positive. Then I take another quadratic extension of F, but this time I'll be totally imaginary quadratic extension of F. So we usually call it quadratic because degree 4 over Q, CM number field. What it really means is just you take the delta, this here, is negative, and his Galois conjugate is also negative, so called totally negative. So you take these to become totally imaginary. Okay? It is biquadratic if you can take Q just equal to negative integer, say b equals 0. Okay? Otherwise, we call non-biquadratic. So OK will be ring of integers over K. And the same abelian variety by OK reaches simply just abelian variety with an OK action. Meaning, there are lots of endomorphisms of A. So that's called symmetry. Yeah, endomorphism, how big are they? Where you have a OK, the ring of that's about degree 4 over Z module, and embedded there. So there's a lot of action there, sort of nice. This give you a lot of restriction on A, make it easier to understand. So sometimes we call it same type because K have a 4 embedded into C because degree 4. We call same type if the sigma 1, sigma 2 are embeddings such that when you restrict to F, they're still different. You don't want to take a embedding and take the complex conjugation. They don't give you good things. So we want to be the same type. Then from this, you can produce, how you produce same abelian varieties. I just tell you one way to produce over C. How do you do it? You take A to be an idea of K, or fractional idea of K, such that this guy itself is a free OF module. You don't need that, but for my purpose, this is a good one. Free OF module. Then the complex torus, you take the C square, you embed a K to C square, because that's why I have sigma 1, sigma 2. That's the same type is. So the A will be a lattice in there. Okay? And this will be OK action. Certainly what you do, you take sigma 1A x the first coordinates and sigma 2A x the second coordinates. Oh, this is one here. So sigma 1, you x on here, second one x on second one. This will be, you can check this is a complex torus, have OX action, actually is a same abelian variety, is by OK. And with principal polarization, I don't want to explain this. This is extra condition you have to do to make things work. Okay. So what about the facts about how this kind of abelian variety is good for? So here's some facts. In general, we have an abelian variety. Surfaces actually are determined by so-called 3 Igusa invariants, J1, J2, J3. Very similar how you determine Hilbert curve. We determine Hilbert curve over complex number field or any algebraic closed field, you just need his J invariant, one J invariant. Here you need 3 of them, because this is more complicated. Okay? And the Ji is equal to infinity. Of course, J, taking Hilbert curve, his J will never be infinity. But if we take this abelian variety surfaces, it could be infinity. When it's infinity, is A is isomorphic to product of 2 Hilbert curves, called degenerate guys. Okay. So factor 2 is, if they're not infinity, then you actually this abelian surface can be written as a Jacobians. Oh, that's a bad J. This is different from that J. This is Jacobians of a J2 curve. And actually, even more than that, so Krusny taught me how to give me a C, give me these Ji's, you can produce actually a model for C. That's important for practical purpose. You can really write down what the C, the equation is about. That's amazing thing. You cannot do that in general abelian varieties. It's very hard to do these things. Okay. So for a same abelian variety, Sven says this guy equals infinity if and only if K is biquadratic. So then from now on, we just assume it's not a biquadratic, because that C is not very interesting. Basically, you're talking about Hilbert curve. Okay, nothing really new showed up. So what's good about same abelian surfaces? You can take any same surfaces. What's good about this? Because they are very concrete. You can sort of compute. First thing is, you took this guy here, you take the J. When we constructed really more like a complex manifold, defined over C. Actually, not defined over C, that's defined over number field. That's why we're happy with number series. So they're algebraic numbers, and this C can be explicit. We explain that in terms of Ji of A. Then you find, well, they're all in number field. Then you know what will happen. So A is defined over number field. That's a sort of a very down-to-earth proof. The same abelian surfaces are all defined over number field, because they're J invariant different number field. Okay, so that's cool. You can start with somewhere. Second, you take a P to be split completely in K. Then you first see that it does not divide the denominator. You see this is the algebraic number. Then you take the norm of the guy, become an integer, or no, rational number. If P does not divide the denominator of the rational number, then you take A to be the reduction of A mod prime about P. Then you can tell you this A tilde will be also abelian variety and also Jacobian of the C tilde. Because the JIs are not, because you say if it's not in the denominator means, what I means that your mod P is not infinity. If mod P is not infinity, then it's also Jacobian. The Jacobian is just exactly the Jacobian of C mod P. And turns out C mod P is also a genus 2 curve instead of have a singularity. Don't have a singularity. That's cool. Not only that, so you give a very nice one. This is what you really care about it from cryptography point of view. Number theory, we want to just care for number theory, but you really very care for FP. These guys, that's why it's going to be split completely. The L will be also, the P also split completely in L, and this will be a abelian surface defined over FP. Okay. Then you ask the question, what's this guy here? And using complex multiplication theory, you can really give a good handle of it. So this guy gives you two good things we need. Abelian surface, you have explicit construction, write down equation. Second, you can bound, or you really just found the how to compute the number. You hope they got to be a big prime. Just compute them, see what it is. So we can do it. So this is very good. That's the reason why they use this genus 2 CM abelian variety, abelian surface. Okay. So the basic question will be: first one, which prime divides the norm? And second, how you bound this denominator. The first one is obviously very interesting, right? Very interesting. That's so the curiosity first ask the question, what's this boundary? It's a very interesting question because you know where you want to do. Secondly, also important, he had explained to me, I don't know why I care about that. He explained to me, this is important when you try to compute them. Because this algebraic numbers, the JIs actually is, you write a function really is a complex function, is free expansions, even approximations. You cannot really just compute them. If you know the algebraic numbers, you sort of can, using floating kind of method, you can compute them. But if the integer is easy, but if it's a rational number, you have to know what the denominator approximately. You have bounded denominator. That's why I have the bounded denominator. So you need to solve the two problems. So that's what she wants to solve. And here's the question. She has a very insightful idea about what the P should be. Assume the dk is the discriminant of your number field. Dk is always given by d squared and d delta. D is not the integer. And then if no P divides the denominator for the same abelian surface described above, then P have to divide this integer. Okay. For some integer m, for some integer n, such that the right-hand side is a positive integer. And here, this inside also have the positive integer too. I should say that d squared minus m should be smaller than d. So the square root of d. So this is not a big condition. If you think about it, it's really only finite many conditions are there. N is bounded, m is bounded. Okay. So if you don't satisfy the conditions, every abelian surface you got are good. Okay. And in particular, you know P has to be smaller than d times d delta divided by 64. You take n equals 0, m equals 0. Okay. So this basically, if you take, I don't want to take it, but if you take a P, it's bigger than this number, then everything is good. Okay, everything is good. So that's her conjecture. And she also made a progress on this with her co-author Cohn, is saying the P, if P divides this, then P have to be d squared, a little bit bigger than that by square, and trace delta square. Trace delta is the delta we said a plus b squared of d. You take a trace, and if k equals this here. Okay, so that's a very nice progress. It's not too big here. And this d delta typically should be bigger than trace d. So now, I'm going to say today's talk I want to be just prove her conjecture, and also bound his denominator when d and d delta are both other primes. That's what I want to do. I want to show you how to do that. So I want to set up notations and conditions. K will be non-biquadratic quadratic same number field, and as explained. And we also assume d is d squared d delta. Both d and d delta are primes, count to 1 mod 4. Okay, that's just the technical condition. And I also want to be okay to be a free OF module, make my life easier. This is technical. This is sort of important somehow. If not, you have become more complicated. And to give a condition of this, you actually need something called a reflex field. Is take the delta and delta prime. Prime means the Galois conjugate. This is another quadratic same number field. And he has a real quadratic field is d delta. That's the delta here. Really, this is really equal to delta times delta prime up to a square. So that's also another reason why we need k to be non-biquadratic. Otherwise, this will be just quadratic, and this will be a q too small. Okay, we can deal with that, but become more another different story.
D and D don't have to be co-prime.
No. When this Galois, they're the same. For example, if second they're the same. In general, we don't need to be could be the same and could be different. If the same is Galois second extension, if it's different, then it's not even Galois. Sort of interesting. This first non-Galois thing you can do. Okay. So I want to define some numbers. These numbers come from arithmetic. It's come from the k delta and the f delta. It's come from reflex field. This sort of like strange at the first thought. Then really it is not too bad, because every time if you take a Hilbert curve, so only have one quadratic field that showed up. Because you just get the field and everything there. Once you start with the same abelian variety, they always have the same type. The type will tell you really the abelian variety is not defined over k. It is defined some extension of the reflex field of that type. So it really has to deal with the reflex field. It have no other choice. Okay. So what you do is you first sum over all the primes, only 1 or 2, on f delta, so divides above p. Secondly, you look at all these numbers. This is only Feynman name because absolute value of n is less than m squared of d delta. So only Feynman, m is fixed. M is fixed. And this d, k delta, f delta is called a relative different, or relative discriminant, the inverse. Okay. So this is some number we define in the next slide. Is this. Bp is either 0. It will be very easy if the p split in this k delta. You don't need to do anything, just 0. If non-split means ramified or inert, it's also very simple. Just look at this prime t. Just look at its order, plus 1. And log p just means his norm. Okay, it's norm. Then take the log. Okay, and this part is the counting function. This counting function. Okay, let me tell you what's this guy here. So first, let me realize this here. T times d of delta of f prime. This will be in OF. Is the integral idea of OF. Okay, and you can multiply by p. That means this guy also have to be a multiple of p. Otherwise, you get 0. So this rule of A is just counting from given ideal in A in f delta. You count how many integral ideal of k delta, such as norm equals your ideal. This is a local condition actually. The count you can write a local product. So, but actually just count. You get a computer program, You got the two expression this, just compute them. They showed up, give you answer, integers, and log p. So log p cancelled. So b and p, I want to emphasize that b m of p really is a positive or zero integer, non-negative integer, really integer. Okay. So I tell you, so bm is equal to n up. That's also fundamental because for almost all p, this got to be 0. So here is a theorem. I want to explain how it is conjectural. And above conditions, and let A to be a semi-abelian surface with OK action defined above. Okay. Then, and take the norm of my J invariant, Igusa in J invariant, take a norm, and you can write it M, I, and Ni. Then, you can really tell what's n1 equal to. n1 is a factor of this. Okay. This looks complete, not really, because this guy just log p. So exponential and take the log just really cancelled. Really just something p to the b. I write it better way really. I should be writing more nicer. Can I write it here? Do I have anything? Okay. So really just the p of b of this guy p. Power and time this multiply there too. So this is a factor. You really have very nice way to run the WK. I explain in a minute. N2 and 3 will be just instead of 6 will be 4. Okay. And WK is the number of roots of unity in K. Typically it's 2. The only one special case is 10. It's K equal to Q joined over zeta 5. So really it's just 2 or 10. That's all. Okay. So these are really just integers that tell you here. And this is a slight refinement of a Christian conjecture because we not only give you which prime, also tell you what the bound is. So the boundary, the really boundary is a factor, of course, smaller than or equal to. Okay. And why this is true here is because if you look at this guy here, dn of this is because if you look at, let me back. Oops. No, back. I think I put it there. Put it wrong place. So if you look at this, b of this guy should always look at this way. And this only thing that happens is this square minus m squared d delta divided by 4d will be a multiple of p because of this here. That's the p was useful here. Okay, so p have to divide this here. That's what the condition is about. Okay. So that's settled. His conjecture. How to prove it? I will give you a rough idea how to prove it using arithmetic geometry. So you really don't think each one. The point of this arithmetic geometry, the modular space, is you don't think each abelian surfaces or curves individually. You put them together, think it's a part of a bigger group. That's called modular space. Let's take x1 to be modular space of curves. Okay, that we know, the well known. Really, if you look at his C points, really the same thing as the upper half plane mod SL to Z. That's when we end, this is the same thing as P1. So what you take tau, the complex number, upper half plane, you just produce a Hilbert curve. That's you should do. You take C mod a lattice. Another hand, what you do, you take the J tau. That's why the J called J invariant because J basically determines the Hilbert curve. This also thinks that J, because of rather this way, he also is a modular function. Okay, that's why you really should think. Similarly, you can look at our abelian surfaces, a modular space of abelian surfaces. That's a very complicated thing. But if you add another thing called principal polarization, then this is a very good modular space. What it looks like? It looks very good. Oh, this X rather wrong way. This is a Z upper half plane, and you SP for X on there. And this in this case is a theorem of Igusa, in probably even earlier, is congruent to is isomorphic to P3. So the 3-manifold is much more complex than this, but still P3 feel much better if you think other things. So how do you do that? What does this mean? You take each tau is 2x2 matrix self. You just do like this. This is Z2, you times tau is another matrices here. So this is C squared like this. Then these are abelian surfaces. And what you do, how you identify them with P3, you take J1, J2, J3. That should be A3 if they're not 0, but sometimes infinity. That's why you think it's a P3. Okay. So what's H2? I want to define it quickly. H2 is just a symmetric 2x2 matrices whose imaginary part is a positive definite matrices. That's all. If you think your upper half part, you think is a symmetrical matrix of 1x1 symmetrical matrices, and imaginary part is totally positive. That's the exact same. Okay, how do you X? SP for X like this. You write A, B, C, D. But A is 2x2 matrix. Everybody is 2x2 matrices. In SP4, AX, how you add A tau plus B. Then C tau plus D inverse. I cannot write divide because I don't. Order is important in matrices. Okay, so that's what the range is about. So this is Z equals 3/4. So what's the J1? I will have to tell you what the Igusa looks like if you see in terms of tau. If this is a modular function when it's SP4 invariant. That's called functions. You can write a fraction of two stuff. Okay. If you look at the denominator, it's very cool. It's called chi10. Have a very good name. Chi10 to the 6th power, and chi10 to the 4th power, and chi10 to the 4th power. That's why the 6 and 4 showed up in the differently. The N1, N2, and 3. The F2, F3, and 4. F1, F2, F3. What that is? Chi10 is a very famous holomorphic cuspal zygomodular form of weight 10. They call it chi10. It's given by Igusa. People are going to call him Igusa chi10. I don't know if he like it or not. The F1, F2, F3 are just the modular form, holomorphic modular forms of weight. This will be 60. This will be 40. This will be 40. They're all very explicit. You can compute. Okay, but they are free expansions. You cannot just plug in to get an exact number. You have to get approximation. Okay. Another good thing about this is chi10 and Fi's have integral free coefficients. If you write free expansion, the coefficients are integral. What this tells you? This tells you actually these divisors. Even though what divisor means the zeros and the poles. There's no zeros, are just no poles, just zeros. The zeros are divisors on the arithmetic fourfold, and not just in the complex torus. So it's very nice. It's really you think this you define over Z, then this will be fourfold, because over C is threefold, over Z is add 1, because Z itself is a curve. Okay, so this kind of divisors very nice. And so what makes the theorem work? Really two things. First, is the chi10 is a very beautiful thing. It's not only because Igusa found it, also he found that the divisor is nice. His zeros, you know where the zeros are. The zeros are two copies of G1. The GMs are so-called mth Hilbert surface in X2. Not forget in general, G1 is very easy to explain. What's that guy equal to? Really just all the CM abelian surfaces who cannot be written as Jacobians of just two curves. They are product of two equal curves. So it's very explicit to construct them. Let's make this so nice, make it work, see it works. Okay. So, but on the other hand, the problem of making the theorem imperfect, because you see the theorem said Ni are factor of this guy, right? I didn't say. I hope I want to say the guy is equal to. That'd be a much better theorem. And I cannot do that because I don't know anything about the divisor of Fi's. If I knew them, I might have a good chance. Especially if the divisor you can describe nice in terms of Hilbert surfaces. If you can do that, it'll be done. It'll be much nicer theorem. Okay. So that's the idea of this. So what is showed up?
Divisor of Fi help you? I mean, if you knew.
Oh, because if you know the GMs, my proof will be really give exact formula. Okay, I'll show you when I prove it, give you see how the. So it's hard to find, generally it's very hard to find zero in the product modular form. Even for the classic, you take a modular form. J, you know how to do it. Zeros into the poles. And I said C of the E4, you know that. Not many other you know, really. Third, you know it. Third function, that's pretty much you know. The others is very hard, okay? So let's give you a rough idea how to prove this. I look at the Cm of k I define to be modular space in X2 of same abelian surfaces of the with OK action and with polarized principal polarization. That's basically take all these same variety I constructed over C range, just take them, you add them up. Actually, it's twice of them because I didn't tell you what the same type is. Okay, so really just that add up. Then use a simple idea from arithmetic geometry called Arithmetic theory on arithmetic intersection theory. You can see that if you take this one, take J1, okay, you really take, instead of trying to norm, that's an integer, I just take an absolute value, positive or negative, and you take a log of them because I want them additive. And this is just a number you deal with. It's 1 over, which this is from here to here didn't do anything. Just tell you Cm of k is double of all the abelian variety defined. Put them together. That's a 2 become 1. That's all. Okay? The J1 of A, the different A's. Here's even that A run all of them. The norm really tells you to all the A's together, or the conjugate really come together here. Okay? So you compute these and use arithmetic theory, really very simple, just definition actually. It's just computing the arithmetic intersection between the divisor of J1 and Cm of k. This is on the X2, the script X2. This is dimension 1 because only finite many points over C. Z is dimension 1, so this is dimension 1. And this divisor in C is also divided in Z, is this dimension 3, because it's one dimension dual, just one equation, so dimension dual. What does it mean arithmetic intersection? It means this. Let's think of more complex ones. You have a manifold, let's say 4-dimensional manifold, okay? You have a 3-dimensional manifold floating around, family of 3-dimensional over there. You have another curve. If that, what do you mean by the intersection? Which is very intuitively just means that so you have a curve, you have a 3-dimensional, what is instead in terms of points in general. If the line is right, okay, point, just count how many points there. That's all. So arithmetic intersection is the same. It's the same. You have over Z, you have a manifold of 4-dimensional, really is 3-dimensional over C. You take 3-dimensional there, take 1-dimensional here. They don't intersect over C, because over C, one is 2-dimensional, another one 0-dimensional. Over 3-dimensional, they don't intersect. So only intersect in terms of each P. For each prime P, they might intersect, because the points might become in your manifold divisor. So for each P, you have to understand we count intersection numbers. But a different P, you should count differently. Okay? It just makes sense. So you can add a weight log P. You count how many points are there and just log P. Okay? Yeah?
The Cm of k, so you say that's a moduli subspace of X2. Is that a subvariety or a quotient variety?
No, it's just you take, so you just count. So what's X2? X2 is you just take all the same abelian surfaces, right? And this one you take the same abelian variety with complex multiplication.
Okay, and does it have a geometric description?
Yeah, that's the geometry. You just count all this. X2 itself?
No, I mean, the Cm of k, is it a subvariety of X2?
Yeah, subvarieties. No, it's just a bunch of, over C is a bunch of points. So it's a closed scheme of dimension 0 over C. Is closed dimension, close the subvariety of dimension 1 over Z. Okay? Because for each P, you also want to find it. So this is really some AP log P. And also cheat a little bit when the intersection over C is very easy, just instead of count how many are there. You also have multiplicity. The multiplicity over FP bar is a little more complicated. You have to do deformation up. But that's just, roughly speaking, just like that. So AP log P, some of them. Now,
That first equal sign there,
Yeah.
that's like, no, sorry, the
This
next
one?
line, yeah.
Yeah.
So that's the content here, the hard part. Is
no, that's not hard. That's very easy.
So how do you, like, when you define Arkelov intersection theory, do you define it in terms of like some green function?
Yeah,
or
but
something like
so
that?
this is the green function because the J1s are rational function. So he's an intersection with this guy over the 0. So one part of the arithmetic section, this is infinite part of this intersection. This is the final part of the intersection. And because the Ji's are rational functions on the modular space, right? So his intersection over 0. That's why the infinite part equals the final part. That's exactly what they did with Gross and Zagier. They come the final part, they come the infinite part, they check they're the same. The reason for them to check is they want to prove a much bigger theorem. So you just want to show the right. The answer is right, so be happy. So for us, we don't need it, we know it's 0. So the infinite part equals the final part. It's based like this. Okay? So now just compute this part. So what's this guy? We just write a J1 equal to F1 divided by chi 10 to the 6th power. So you really just equal to divide over F1 minus, because denominator, 6 times divided over chi 10 times CM. Okay? And this part I don't know what to do, still put there. And minus the chi 10 divisor is G1. 2 G1, so 12 of this guy here. Okay? That's what I really want. So to compute this, really I have to compute this part and this part. Okay? This part. That's really the beef here is try to compute this part and compute this part. So what I can tell you is, only thing I can compute is this part, the G1 part. And actually I can compute GM. If I take GM, you compute this equal to this guy here, equal to the summation of n bigger than 0, this is bigger than 0, and dm minus n squared over 4. So here I'm changing m should be m and times d should not be a square. Then otherwise I have been in trouble. Okay? This number I defined before. This arithmetic log p here. So that's what I can compute. That's the main theorem I used, I proved. Okay. On the other hand, this part is positive or 0, because it's count intersection numbers. Okay. And this f1 and the CMK that don't intersect at the over C. So really this is this is effective numbers. So really is positive or 0. Okay. So let's see what you get now. You look at the back. See here, this is equal to this, right? This is positive or 0. And this is, we know how to compare. So this is less than equal to this guy here. That's the reason. And you actually know that this AP is not P, so this you know direction. This guy is a divisor. That's the reason. That's the proof. That's a simple proof of this. That's the idea. Okay. Any questions so far? So now when we that's how you prove this Lauter conjecture. Now just repeat what I'm saying. F is the same abelian with O action as above, and this normal this. Then this will be a factor of this guy here. That's why it showed up here. And n23 is 4. This 4 is come from that chi to the 6th power, chi to the 4th power. This WK equal to 2 or 10, not very important. And this is the formula you can compute actually. So give you a bound. Not give it, but really give you a factorization of this. It's a factor of this guy here. Okay. So how do you prove that? So now I want to do another 10 to 20 minutes. I want to tell you how to prove that theorem. I want to tell you the arithmetic intersection formula, purely geometry. You take a scene there, and you compute what's the intersection. Okay, that turns out to be a very hard question in general. Is see the x2 is huge. It's a 3-dimensional manifold over C. Then you go over Z, it becomes 4-dimensional thing. That's hard to deal with. The divisor is a 3-dimensional thing, and you got another one dimension you want to insert is very hard. So another hand over curve is much easier because the original only just 1-dimensional. You put a 2-dimensional, very simple. I want to cut those curves. You cannot do it, but there's something in between 1-dimensional and 3-dimensional, or from 2-dimensional to 4-dimensional. There's something called Hilbert modular surfaces. So this is where you take a modular space of a binary surface with the OF action plus some polarization. OF, F is a real quadratic field, and you cut it become smaller than x2. So this actually is, you can tell them what it looks like. You tell his C points really looks like H squared 2 copies of H, and mod SL2 of OF. That's called X. This is dimension 2 manifold called surfaces. That's called surfaces. Okay, Hilbert modular surface, because it's 2-dimensional. Here you can see I cannot say equal to P2. Actually, it's not. More generally, in general, F, this guy is called general type, very complicated. But at least I cut to 1-dimensional. That's nice. And how do you act? You take gamma in SL2R, just act as the gamma of Z1 and the gamma prime of Z2. Prime is the gamma conjugate. So that's very much like your Hilbert curves. Here's the cool thing. If you look at the 3 things between x1, x, and x2. X is in the middle, so it's easier. You first have an embedded from x1 to x. You take E, just tensor with OF, this become a 2-dimensional abelian surfaces. Certainly have OF action here. So that's a cool thing to do. And his image is called his first Hilbert divisor of X. So very nice guy here. And you also have from X to X2. So X, what's X? Is his points are abelian surfaces with real multiplication, right? Just ignore the real multiplication. Just forgettable functor, and you get A, and that's will be your point in X2. And this, his image is also very nice, is the teeth Hilbert surfaces, actually. So it's very nice. So how do you, so now I want to do is I translate the scenes from the X2 to X, because 1-dimensional newer. So let me do a little bit more about the Hilbert-Zagier divisors. This is all the scenes, beautiful thing to start with the Hilbert-Zagier in 1970s. They try to prove some conjecture of Sayre and include all these divisors here. These are also part of Schmal varieties. They have divided. So you take quadratic space. V is a 2x2 matrix in F, such as the transpose equal to the Galois conjugate. If you compute like the A, B, lambda prime. Okay. If you take the quadratic form, and this will be A, B, this is the 1, 1, this will be also 1, the signature will be 2, 2. Okay. And if you care about this, if you use this quadratic space, you do Schmal variety, you exactly get a Hilbert modular surface. And take a lattice like this, A, B, and A, B, and Z, lambda is in the different inverse. Then you can define some curves inside these varieties. What you do, you take any A in this kind of thing, the determined positive. You just compute this quadratic equation. And this will be a curve in copies of H2, H, and I small to H. Why is that? I need to give something very explicit. You write them down really like a quadratic like this. Okay? Then if you do it again, Z2 really determined by Z1. So that's why the 1 copy of H, but twisted. The twist is important. Okay? So what's so-called a Hilbert-Zagier divisor is very simple. Just take all the A's, such that determine equal to M over D, it's FA. You take all of them, you take SL to OF action there. That's where we give you a divisor. What that is? This guy's empty if the neuron symbol is negative 1. And in general, it's just the final union of curves in X otherwise. And they are Schmal curves or modular curves. Some not Schmal curves, some are modular curves. Okay? And T1, what we decided before, this is really just diagonal mapped here. If you write a phi 1 carefully in terms of over C, really just Z mapped to ZZ. Just that cool. Okay? And if Q is a prime splitting F, then the TQ will be looks like a twist embedding of the open modular curve Y0Q. The modular curve embedded to the Schmal curve, or to the Hilbert modular surface. In general, it's more complex, sometimes Schmal curve, not just the modular curve. Okay? So we pull back, so I'll try to explain how you do this in, let's call TM, something called closure of TM in here. Oh, this is wrong. This is in X. This is X. Script X is the Hilbert modular surface. Then here's the beautiful thing what we can do. You take the Hilbert surface, that's what I want to understand, because we care about the Hilbert. Really, Pullback, this guy, phi2 Pullback, is really equal to this, the Hilbert curves. That's what we use to understand the thing. And this is dimension 1 over C, dimension 2 over Z. 1 dimension lower than GM. Make your life a lot better. Okay? And CM is, if you have an OK action, certainly have an OF action, so you can also think it's the same cycle in X. Because K is bigger than F. Okay. So then you compute them. This is what I want to compute my theorem. Really become Pullback to in X2 in the section. You can switch it to X in the section here, Tm. Here the M will be set by all these conditions here. This kind of M really just really be dm minus n squared over 4. So here the summation is. Okay. So this should be wrong. M. This should be n. No. This is m, and this should be n. Some kind of like this. Okay. D of this m should be equal to dm minus n squared over 4. You sum all this in terms of all the n's. So that's how our type of the first term give it to all of them. So the main theorem I want to compute is the Tm. For each Tm I know, then I take a summation, we get add-on. So Tm will be equal to this. If it's assumed the OK is a free OF module, and also the prime, that's what we assume anyway, then the arithmetic intersection on this Hilbert modular surface is equal to half of Bm, the Bm I defined before. That's where if you haven't used this theorem, then you can get back to that theorem. So really we're working on the Hilbert modular surface instead of that one. Okay. So how do you do this? So even that is sort of hard actually. For general M, it's very hard to do because the Tm is hard to describe. Sometimes the Schmer curve, sometimes the modular curve. Schmer curve is a very complicated thing to do. It's very hard to describe. Okay. So it's hard to compute this in general. And what I did is use some trick. We compute some, what I can, others I use modularity. So first one, I compute a weaker version of this. Okay. What's a weaker version? You take the same idea, but you only, instead of take M, you only take the prime splitting F. That's why you have a modular curve, you have a really static curves. Then I can compute this guy equal to. I cannot do it actually, even that I cannot do it. I can only figure out equal to half of BQ. BQ is whatever, this is what it's supposed to be, right? But I don't know what happened with Q, the Q place. So I say, well, I don't care. Just I know it's different by log Q by some rational numbers. Later on, I just argue from general theorem, this CQ has to be 0. I'm done. So really, very weak version. First, I have to be split. Then even split, I don't care about the place at the Q. Okay, that's what I proved. This is really how to do computation, really seriously do intersection theory. Okay. The others is not. Others use the version. Then what I do is use the same value for some general formula approved by Bruni and myself. And then use this arithmetic intersection theory I just explained before. Use more general, not just the degree 0, the rational, very general machine, you have to use them. Then plus modularity of Borchers. This guy, we take these, T0 and Tm, put them together, actually is a modular form with 2. When using this here. And this better tell you this. And this also same as H2. I realized that when I talked to Christine this morning, usually this is not really a Borchers result. It's already known by his brands again. Okay, his is much more general. This in this case also there because CH1 really is the same thing as H2 in this case. H2 cooperative group is easy. Okay, there you tell you, but I tell you these TMs, you don't need the word TM. They are really a linear combination of fundamental TMs, and you can take that fundament to be the split guy that I talk. So that's why you don't need the fundamental TQs. Then you can just take the other just linear combination of them. The machine of these guys, they're linear. So you don't need to deal with everything. That's the trick. Okay. So you need then the arithmetic group that's done by of Brunier, Berger-Gill, and Cohn. Okay, and then you divide the general case. So what's the formula I talk about in this second part? It's like this. You have this guy here. You don't need to be free. You just take any modular form. If integral coefficients, and normalized just means if you take all the coefficients together, you take a GCD should be equal to 1. And such that his divisor is known. If you know his divisor, then you are happy. If his divisor is equal to the linear combination of TMs, then their value, this value really just you take the product and take the log. The Peterson here, I'll explain in a minute, equal to 2 parts. One part is what we got here, you see here? Here. And the other part is very transcendental. Okay, this is the part I wanted. Anyway, this is where I want to prove my original one. Okay. So first, I will explain to you. So first is the Peterson norm. Metric really just means you take the absolute value. But that's not well defined if these are not the function in the form. So what you do, you take y1, y2, and take the k over 2. This 16 pi squared is just the normalization makes things nice over z. Okay, the beta is a very weird thing here, but very transcendental, you can see. Gamma is our Euro gamma function. Look, 4 pi is transcendental. And this guy is also supposed to be transcendental too. What's this guy? Well, you take the Heck character chi of k over f. That's associated to the quadratic extension. And take it as a error function, you complete it. And that's it. As a log derivative of this. Okay. This actually is another theorem. This part will be equal to, we proved in the, once I prove this is also equal to the height of your abelian surface. The height tells you how complicated this guy. This actually is called non-abelian Chowla-Selberg formula. Chowla-Selberg formula is a very beautiful formula in 1950s when rephrased as integral curves of height of same integral curve equal to something like this. Okay, and this is the part of a conjecture of Cohn. So that's what I've done there before. So that's really, see, use that theorem plus that before we can prove the theorem. I don't want to get detailed. Okay, so this, I'm going to tell you some couple of minutes to tell you other applications. So one application is to what just 2 curves. We talk about that, the J invariant. You can also talk a direct geometric language. Okay, it's like this. If a K quadratic field as above, if you have a C is a just 2 curves over number field, such that his Jacobian is have a CM by OK. That's exactly what we do, right? Exactly what we do. And this kind of always give you principal polarization. And if has a good reduction everywhere, the abelian already have good reduction everywhere. That's always true. You can always do that. Same abelian variety, you can always make it good reduction everywhere. However, take L to be a prime, the P. If C has a bad reduction at some prime above L, even though the Jacobian have good reduction everywhere, C sometimes don't. What can determine by the denominator of chi 10, basically, the denominator of your J variant. That's exactly what you're really saying here. If I have bad reduction at a place, then must be set up as a condition for some of this guy here, this is not 0. Okay, that's because the bad reduction means that P divides the norm of that guy, and that's a factor of this. So if that one, this cannot be 0. Okay, that's the idea. Conversely, if this is not 0 for some of these are here, then there always exists just 2 curves set of condition. Now realize that talking about this here is actually for every curve, they can always have a better reduction over some prime because they all conjugate to each other. Not all the prime, but some prime. Okay, it's here. And the idea is C has a better reduction if and only if the JC Jacobians of the hammers intersect the G1 at P really have intersection points. That's the B1, B give you about. Okay, that's the idea. So another application I just mentioned briefly is give a non-abelian generalization of celebrated Chowla-Selberg formula. Okay, I don't think I want to give you a proof of the work version. I want to say I want to give a proof. I don't think it's a time is already over. I don't want to. If you want to know, I can explain to you later. But I just stop here. Thanks a lot.
Other than for me? Okay, so let's thank Tong Hai again, and we're going to go and have lunch in the cafeteria.
Thanks.